This is Luke Masella. He shouldn't be this healthy.
I was born with spina bifida, which is a birth defect. It's basically a hole in the spine where all the nerves don't develop. When I was 10, I got really sick, and they were trying to figure out what was going on. And I was in and out of the hospital every week, and they finally figured out that I was actually in kidney failure.
A faulty bladder was Luke's problem, caused by the spina bifida.
The bladder was sending fluid back up into my kidneys, which was making them not work correctly.
But Luke was given a remarkable treatment. At Wake Forest School of Medicine in America's North Carolina, researchers are growing artificial body parts. Luke was one of the first in the world to benefit.
They take a piece of your bladder out, they grow it in a lab for 2 months into a new bladder that's your own, and they put it back in.
Grow your own organs in the lab means no rejection problems and no waiting around for organ donors. It's called regenerative medicine, and it's an exciting future that awaits us all.
I see us getting to a point of having options available that actually stop disease processes, reverse disease processes, or offer people cures.
Simple organs, like bladders, are the easiest to grow. Cells were taken from Luke's original bladder, multiplied up, nutrients added, and that produced this pink solution.
And we then created a three-dimensional mold, and we place the cells on top of the mold.
The mold is in the shape of a bladder and is made from material that breaks down in the body.
We placed the mold with the cells in an oven-like device. We cooked it, if you will, very much like baking a layer cake. And we then were able to take that organ out, and we were able to place it into patients.
And the team has cooked up more than bladders.
Another of the organs that we have targeted is the urethra, which is the channel that connects the bladder to the outside of the body. It is a very important organ, as you can imagine.
Some of Anthony's patients had had car accidents, damaging their urethras. So he decided to grow them new ones. They were like bladders, really, with a different geometry. Scaffolding was seeded with the patient's cells and nutrients, and then sewn into the shape of a urethra.
And we then were able to place those engineered urethras back into those patients.
To automate organ making, the researchers came up with an incredible method. Print them. They even started out with modified computer printers.
But instead of using ink, we use cells, and we print the cells with a gel-like material, one layer at a time, and we then allow the gel to get harder over time.
Nowadays, these bioprinters are purpose-built and much more sophisticated. Indeed, on the other side of the country, in San Diego, we visited startup company Organovo. They're planning to take bioprinting to market. Very impressive looking labs, brand new.
Brand new, been here for about 3 weeks. This is where the action happens. These are our tissue culture hoods. It keeps everything sterile, and we take the cells and build the 3D tissues within this space.
So it's kind of an organ growing lab in a way.
It is, absolutely.
This sophisticated robot is the bioprinter. It squeezes out 0.5 millimetre wide cylinders of bio-ink. The ink's just clusters of human cells, remarkably holding themselves together in the correct shape, just with natural adhesion. 6 cylinders of cells are laid on each other to make a tubular blood vessel. In this cross-sectional diagram, the red circles represent the walls of the vessel.
This is a fully human blood vessel that we've created with the bioprinter here on the plate. And so you can see its three-dimensionality just as you turn the plate at a slight angle.
Again, the cells have assumed their correct positions in the vessel by themselves. There's no scaffolding holding this together. So how do the cells know where to go?
They're smarter than we are in a lot of ways. It's their inherent properties. I think it's it's leveraging the qualities that cells naturally have, which is to stick to each other. We are able to control the shape in which they do that, and then the printer builds the ultimate structure.
The next step is to give the cells nutrients and then put them in the incubator overnight. There, they'll continue to self-arrange and form a vessel. After a night in the incubator and with a bit of cleaning, this is what you get. A replacement blood vessel made out of your cells. This blood vessel is the width of a few human hairs. Back in North Carolina, they're developing another application for bioprinting, for wounds.
And one of the strategies is to have a printing machine that not only prints but also scans. So basically the patient is first scanned. So the wound area gets a scan of the wound, and then we're able to go back with the printer and print the right layers of tissues right where they belong.
Now, for most organs, there's still a long way to go before they'll be ready for patients. But research is progressing on artificial kidneys, heart valves, large blood vessels, and skin. Here it's being slowly stretched out. They're even working on artificial ears and fingers.
Of course, fingers is still a long time away of us actually getting that into a patient. But the ear is simpler than a digit, and we're creating ears in the project we're doing right now with the military to provide these kinds of structures to our injured warriors.
Even muscles are up for replacement.
To create artificial muscle, we use the same strategies as we have used with other tissues, but we also exercise them. We put them in these small bioreactors, these exercise machines that actually stretch and compress the muscle structures so they build up strength over time before we implant them.
But the organs most in demand are kidneys and livers. And Anthony's team recently had a breakthrough. They developed miniature livers that functioned like human ones, in the lab at least. But artificial liver and kidney transplants are some way off because they're so complicated.
The kidneys have a very complex structure because it's a solid organ. And so unlike other structures like flat structures such as skin, which are the simplest, tubular structures like blood vessels or urethras, which are a second level of complexity, or even the bladders, which are a third level of complexity, the kidneys are a solid organ and have a fourth level of complexity. And therefore you have a lot more cell types, so it requires much more sophisticated methods for engineering.
Still, fixing up livers and kidneys may be closer than you think. We may be able to patch them.
If you take chronic kidney disease, for example, by the time a patient shows up at the doctor to say that I don't feel well, they are usually down to less than 10% of the function of that organ.
That says you don't need the whole organ to be replaced to feel well.
The tissue that is required to replace is actually only 10 to 20% to change the way that patient feels, change their quality of life, and really be effectively a cure for them.
Predicting the timing for any research is always difficult, but it's clear some pretty exciting developments are on their way. There'll be so many people like Luke who will benefit.